Ever wonder about infinity? How can something be endless? And yet, can there be more of one endless thing than another? These questions may seem more like philosophical musings than mathematical inquiries, yet they form the basis of some of the most intriguing concepts in mathematics. Infinity, in its simplest form, is a state of endlessness. It's a concept that most of us understand superficially, a line that goes on forever, a number too large to fathom, a time without end. But mathematics takes this concept a step further and introduces a paradoxical idea. One infinity can be larger than another. Imagine two sets of numbers, both infinite, yet one somehow contains more numbers than the other. It's a conundrum that challenges our basic understanding of quantity and size, pushing us to redefine these concepts in the context of infinity. It's a strange thought, isn't it? But this is the magic and mystery of mathematics. Opening. Take a moment to think about the number line. It's a simple concept, but it holds an infinite world within it. Now let's break it down. The number line is a visual representation of all real numbers as points along a straight line. We usually place 0 at the center, and from there we can go in two directions, towards the positive numbers on the right and towards the negative numbers on the left. But here's the catch. While the line itself is finite, confined to the width of our page or the breadth of our screen, the numbers it represents are infinite. You can keep moving along the line in either direction, and you'll never run out of numbers. In this way, the number line is a humble portrayal of infinity. It's like a bridge, a translator, if you will, between our finite understanding and the infinite realm of numbers. Through this tool, we can grasp, at least conceptually, the idea of an endless set of numbers. But what's even more intriguing is the infinite nature of the numbers between any 2 points on the line. Take any two numbers, say 1 and 2. Between them lies an infinite set of numbers. These are our decimal numbers, fractions, or more technically, the rational and irrational numbers. The decimal 1.1, the fraction 3.2, the square root of 2, they all find their place between 1 and 2. And the number of such numbers is not just infinite, but mind-bogglingly so. We can always find a number between any two numbers, no matter how close they are. Isn't that something? So, the number line, in its simplicity, represents an infinite quantity of numbers. It gives us a way to visualize the abstract concept of infinity, to map it out in a way that's within our grasp. With every step we take along the line, we're walking into infinity. Closing. So the number line, in its simplicity, represents an infinite quantity of numbers, but could there be more? Scene script. Here's where it gets interesting. Infinity meet infinity. Let's pause and ponder the concept of infinites within infinites. It's a mouthful, isn't it? But don't worry, we'll break it down. When we look at the number line, it's easy to see that there's an infinite quantity of integers. From negative infinity to positive infinity, the integers go on and on. But let's zoom in on any two integers, say between 1 and 2. We see a whole new world of numbers. These are the real numbers. And between any two integers, there's not just a handful of these real numbers. There's an infinite quantity of them. Aha, that's right. Within the infinite integers on the number line, we've found another infinite set, the real numbers. And here's the kicker. This new set of infinite real numbers is even larger than the infinite set of integers. You might be thinking, wait a minute, how can one infinity be larger than another? Well, that's the beauty of infinity. It's not just a concept, it's a landscape filled with endless possibilities. It's like standing on the edge of an ocean, looking out at the horizon. The ocean is vast, seemingly endless, but the horizon, it's even further, even more unreachable. That's what we're looking at here, an infinity within an infinity. And just like the horizon, this concept might seem a little out of reach, a little hard to grasp, but that's okay. Infinity is not meant to be tamed. It's meant to be explored. It's meant to be marveled at. So we've got an infinite set of integers on the number line, and within that, we've got an even larger infinite set of real numbers. That's infinites within infinites, an ocean within an ocean, a horizon beyond the horizon. So there are different levels of infinity on the number line, but how can we make sense of this? Enter set theory and cardinality, mathematical tools to tackle these infinite complexities. Set theory, at its most basic, is the branch of mathematics that studies collections or sets of objects. These objects can be anything from numbers and shapes to more abstract entities. But what happens when we apply set theory to the concept of infinity? Enter Georg Cantor, a mathematician who dared to delve deep into the infinite. Cantor introduced the concept of cardinality to compare the relative size of sets, even infinite ones. Cardinality, in simple terms, is a measure of the number of elements in a set. Let's consider an example. Imagine a set of all integers. This set is infinite, right? Now consider a set of all real numbers between 0 and 1. This set is also infinite. But here's where Cantor's breakthrough comes into play. He showed that these two sets, while both infinite, are not the same size. The set of real numbers between 0 and 1 is larger. It's a larger infinity. How can this be? It comes down to how we pair elements between the sets. For every integer, we can find a real number, but for every real number, there's not necessarily a corresponding integer. This shows us that the set of real numbers is more infinite than the set of integers. So, thanks to set theory and cardinality, we have a way to compare infinite sets. We can say that some infinities are larger than others. It's a mind-bending concept, but it's also a testament to the power and beauty of mathematics. It allows us to grasp and even quantify the seemingly ungraspable. It turns out not all infinities are equal. Some are in fact larger than others. Infinity, it seems, is not just a simple concept of endlessness. It's a multifaceted entity that paints a vivid picture of the vastness and complexity of mathematics. It's a concept that continually perplexes us and challenges our understanding of the world. When we talk about infinity in mathematics, we're not merely talking about a concept that's bigger than any number you can think of. It's not just a concept of endlessness. It's much more. It's about the infinite possibilities that lie within each number, each set, each concept. It's about the endless complexities that lie within the seemingly simple. As we've seen, the number line, a seemingly simple tool, holds an infinite number of integers and an even larger infinite quantity of real numbers between any two integers. This is a perfect example of the concept of infinites within infinites. It's the kind of complexity that challenges our intuition, that pushes us to question our understanding, and forces us to delve deeper into the abstract nature of numbers. Mathematicians like Georg Cantor have explored these notions of infinitude, introducing concepts like cardinality to compare the relative size of infinite sets. Cantor's work illustrates that not all infinities are created equal. Some are larger than others, some are more complex than others. The collection of integers is infinite, but it's a smaller infinity than the collection of real numbers between 0 and 1. This is the fascinating complexity of infinitude. It's a concept that goes beyond the simple idea of endless. It's a concept that dives into the abstract, into the complex, into the infinitely intricate. It's a concept that explores the rich tapestry of mathematical ideas, revealing the beauty, the complexity, and the infinite potential of numbers. So next time you think about infinity, remember it's not just endless, it's endlessly complex. It's a world of infinite possibilities, of infinite complexities, of infinite wonder. And that's the true beauty of infinity. Let's take a moment to reflect on our journey through infinity. We began with the simple yet profound number line, a tool that visually represents the infinite stretch of real numbers. From there, we dove into the concept of infinites within infinites, an idea that challenges our everyday understanding of quantity and size. We explored set theory, a mathematical framework developed by great minds like Georg Cantor, which allows us to compare the sizes of different infinite sets through the concept of cardinality. We found that not all infinities are created equal. Some, like the set of real numbers between 0 and 1, are even larger than others, like the set of all integers. This exploration of infinity has led us to the fascinating complexities inherent in the abstract world of numbers. In the world of mathematics, infinity is not just a concept, but a fascinating realm where the endless isn't just more, it's infinitely more.